So today we have the lesson for Riemann sums, but this time using the right endpoint. So this is basically a review from pre-calculus where we went over approximating the area under a curve using RRAM. Okay, so these are the two formulas that I had mentioned on the previous lesson. And as I said that there was a formula for LRAM, there's a formula for RRAM. There's actually a formula for MRAM too. Okay, I actually wrote that on the board when I do teach it in pre-calculus. But as we went over the homework before LRAM's lesson, we've noticed, hey, wait a minute, why does the textbook always focus on RRAM? The reason for that is because the RRAM formula, as you can tell with the length of the formula, is much shorter. This is the formula that we use in calculus to approximate the area under a curve. Okay, so that's the one that I want you guys to copy down because you may end up needing to use that later. Okay, this is for when the width is the same. Actually, it could be for when the width is different, but you can see the width is b minus a over n, and I'll describe that in a little bit. So now in pre-calculus, we did have a homework assignment, and so I just want to show you what that was here, so that way you can be familiar with what was done in pre-calculus. So again, it's a review for many of you. You're probably looking at this like, oh my goodness, I remember this. So you can see how they're drawn graphically, which is also very good. It gives you a visual representation of what was explained in the last lesson. So we have an entire increasing function for this interval that I can write. Hold on. And so from the left endpoint over, they all look, our rectangles all look inscribed. So this is an underestimate as far as the area is concerned. So since the width was the same, we're able to factor that out. That is possible. But just a heads up, a lot of times when you're given those tables, they don't have the same width. Sometimes they do, but sometimes they don't. When we get to what's called a trapezoidal rule, and we're not using rectangles, but we're using trapezoids to find our area, you'll see more where the width would be 1 because it follows this process a little bit more than when they just say left endpoint or right endpoint. So we still have a table of values, very similar to what we went over in class. And here I was using fractions to find my area, but then ultimately we ended up needing our calculator for the decimals. So sometimes there are non-calculator sections and sometimes calculator sections that use this process. Usually it's a non-calculator section that uses this. I'm just giving you that heads up. Now, sometimes they're not going to ask about, hey, if it's an underestimate, overestimate, unless you happen to know like what your curve looks like and you can tell based on the rectangles what it'd be. So the reason for that is something like this. So this is a good example where you can see the function, it increases then decreases. So we have some rectangles that are inscribed and some that are circumscribed. So it's very hard to determine unless this is very like strictly easy to tell. I'll show you an example of that in a second. It's very hard to say, oh, underestimate, overestimate. So sometimes you're asked about that and sometimes you're not. So an example where you have a function that is like that. Let's say it increases and then decreases, but a to b is only from here to, let's say, here. So now you can kind of see that once you draw in your rectangles, I'm still kind of going with LRAM for right now, that there's only one piece that may be circumscribed. Okay, so this is still probably more of an underestimate than an overestimate. under, over. So it depends on the function and the interval itself that's given. So let's start talking about like the RRAM and using the right endpoint. Okay, so when you're looking at any function, it can be any function. It can be increasing, decreasing, concave up, concave down. I'm just going to draw something that doesn't even have concavity. And you're trying to approximate the area under a curve from A to B. Here's A, here's B. Maybe this is the x-axis. This is your curve. All right, so you start to create rectangles based off of the width. Okay, so the width is delta x sub I here. And you have what is considered your left endpoint and your right endpoint. So when you refer to the left endpoint, we refer to it as I minus 1, whereas this is I. And the reason this one is I is because from here to here alone, it didn't create the rectangle. But if you go over the correct width, it finishes the rectangle. It finishes your first rectangle. And so that would be a 1 if you're talking about its width. But that's why we would always classify as the right endpoint being an I and a left endpoint being an I minus 1. So now, if you're associating whatever the width is, okay, compared to I, that makes RRAM's formula easier as opposed to LRAM's formula, because then you're comparing it to where I minus 1 is. Okay? Now, if you notice, this is all being plugged into your function value. Okay? This is giving you your y, your height, depending on which one you use. And we're going to focus more on your RRAM today. That's going to be your height of your rectangle. Is a plus A. The reason for that is because we can't always assume that A is going to be 0. Okay, 0 can be all the way over here, and that A value is really 1. Okay, so if 1, and let's say your width is 1, we'll base it off of the last lesson. Okay, and let's say this is not a straight line. Let's say this is x squared. Then the value you're plugging in here, okay, would end up being 2. Okay, so that's how we get our function value. But we leave it in terms of i's because we're looking at a particular rectangle. And again, this may end up just being b minus a over n. So we'll see in later lessons what to do with limits and finding the area under the curve. We even spoke about this in pre-calc. We did it with limits too, so don't get nervous. It's just a basic of limits. It's not new formulas or anything from limits. But again, don't be scared because you already did that. You tackled that. You achieved your knowledge of limits. So they are going to appear again and again until the very end of our course. So please do not worry. They won't be as complex because you went over that, you tackled that, you did that. And let's just continue with RRAM. So formula is important for later. I want to make sure to emphasize or overemphasize that you copied it down. So let's do a problem similar to yesterday, but a little bit different. So it's the same function, and it starts off, A is the same, but I changed B. So by changing B, they won't have the same equal width as before. It won't be 1. We are going to have an equal width, and each rectangle is going to have a width of 2/5, because A is 0, B is 2, and the number of rectangles is 5. So we end up working with a fraction or decimal. If you don't like 2/5, you can use 0.4. That's fine. So I'm going to create a table again instead of a graph. So we're starting at 0. We're going to end at 2. And this time we're going to add 0.4. So if we add 0.4 to 0, we have 0.4. We add 0.4 to 0, we get 0.8. That's a 0, it's a 0.4. I wrote the right thing, I said the wrong thing. We add 0.4 to 0.8, we get 1.2. We add 0.4 again, we get 1.6. And we add 0.4 again, we were already up to 2. It's a pretty big space there, but that's okay. So now we have to plug these into our function, okay? This isn't so bad. It's an easy enough function, easy enough values that we may not need the calculator. So 0 squared is 0. 0.4 squared, okay, is 0.16. And 0.8 squared is 0.64. And 1.2 squared is 1.44. 1.6 squared is 2.56. Okay, so still perfect square numbers. You're just moving the decimal. And 2 squared is 4. Ta-da! So we're done with our table, and if we're using RRAM, then for our approximating area, again, I want to stress how we're using Riemann sums and the right endpoint, okay, this time. So for this particular rectangle, it has the same width, okay, as we were discussing, it's 0.4. I'm going to multiply it by not our left endpoint, but our right endpoint. So it's going to be 0.16. Okay, I have to admit, this is probably where I would use the calculator too. But I'm not multiplying it yet. Let's finish the setup. The width of this rectangle is 0.4. And we're going to use not the left endpoint, but the right endpoint for that rectangle. And that is 0.64. And let's go again. So there's supposed to be 5 rectangles. Sometimes in a problem, we'll say 5 subintervals, so you can make the spaces for it. I'm going to try to do that so I don't run out of space. Okay, next rectangle. So the width of this rectangle is 0.4. The height is based off of not the left endpoint, but the right endpoint, 1.44. The next rectangle, the width is 0.4. The height is based off of the right endpoint, so it's 2.56. And we're up to our last space, so this is the last rectangle. It has a width of 0.4, and we're not using the left endpoint, we're using the right endpoint, so we're using that 4. Okay, so this would approximate our area under our curve using Riemann sums. We use the right endpoint. And this is entirely increasing, as was before, just different interval. And instead of using our left endpoint, we use our right endpoint. So we're going to end up, if we drew this out, with circumscribed rectangles. So this is going to end up being an overestimate, if you were asked. And you can just, again, base it off of your table, okay? Looking at those values, it makes sense if you're using the right endpoint, you're going to end up with an overestimate. So it's sometimes tricky, just kind of make sure it makes sense to you as to what the values are, okay? So now I'm just going to show you this because I show it in pre-calc. If and only if the widths are all the same, you can factor it out. And this might make the multiplying and adding up a little bit easier to do. For some people, it's still going to take them some time to kind of add this all up. But it is possible to do. Okay. Again, you can only do this if the width is equal. Okay, I gave an example in a prior lesson where it wasn't, just to get your idea that it's not always equal. Just for like pre-calc it is. So it would be 0.4 times 8.8. I'm running out of space here. So your approximate area would turn out to be 3.52 square units. I ran out of room. Alright, but we fit it in, and I want you to do some practice problems, so let me pull that up and you can work on those. Okay, so work on these problems for RRAM. And now you're reviewing LRAM and RRAM, and again, we're going to also do MRAM, just to get our feet wet for what's to come next term.